Hi. What we have done already is Boolean algebra. We examined what Boolean algebra is. That was a mathematical sense. Now, here in this chapter, chapter 3, we will be examining the application of Boolean algebra in practice. So there are two areas that we can apply this algebra. One of them is Boolean propositional algebra. In this video we will examine this one, and then we are going to examine application of Boolean algebra to logic circuits. That is the other one. So altogether maybe 3 videos we're going to see in this chapter. Now let's escape from here and then come to this open board. Open board, okay. Here we are. So let's move this a bit that way. So what we are seeing here, we know in Boolean algebra we've got 3 operations, AND, OR, and NOT. So these operations here are also the words in the language, isn't it? Words, language. So the who find the Boolean algebra is George Boole, who lived in this time period. He wrote a book of which name is An Investigation of the Laws of Thought. You see how you can examine thought, find the laws of thought, means you are talking about language. So these operations here are the words that we use in our language. Therefore, it says investigation of thought. How does this help us? Because we explain our situation where we are by using the words. So that becomes critical. By using the words, that means you use the propositions. That means combination of the words gives you a proposition. It has a meaning. So assume that we are trying to design a circuit whether an elevator system is working properly or not, reliable or not. So how we are going to determine that a system, elevator system, is reliable or not reliable? So we can say that we can consider a Boolean function when this Boolean function value is equal to 1, like this. Let's say f we are talking about. When it is 1, it is reliable. When it is 0, unreliable. Here, maybe in here it is the opposite, so let me say it the correct. Let's say when it is unreliable, function is equal to 1. Unreliable. That means a signal is going to come up. That could be an alarm, that could be a light, so it's going to be on. The system is not reliable. When it is 0, it is reliable. So no problem that is. So I am going to write a Boolean function f. So how I am going to write it? I am going to consider now the conditions which represent an unreliable case. One of them is given here, for example. If elevator is running, let me use this blue color for this first case. Elevator running, it is empty and not cold. Assume that there is an elevator, it is running, it's going up and down. Inside there is nobody in it, and nobody called that. So in these 3 cases, that means there is unreliable case, isn't it? So this is one case. The second case is this one here. It says elevator is running once more and its door open. This is another unreliable case. You can increase these cases as many as you like. So let's consider just those two now. So I am going to represent this first unreliable case and the second unreliable cases. How I am going to represent that? I am going to represent those with a product term. How? I will explain to you. So when I use these words here, I am introducing variables. These variables are U, running elevator. Let's say we represent elevator is running by this variable. When elevator is not running, that's going to be U prime. Elevator is empty, we represent it with variable V. When it is V prime, it is not empty. The opposite is non-empty, isn't it? So Y is cold, Y prime not cold, Z open door, Z prime closed door. So how many variables do we have now? We've got U, elevator running. We've got V, elevator empty. We've got Y prime, elevator is not cold. And we've got Z. So altogether we've got 4 variables, isn't it? So my function is going to be the function of these variables. So I determined now my Boolean function variables. Now how I'm going to represent the case 1 for unreliable case. If we say that U is 1 and elevator is empty, V is 1 and not cold, that's Y prime. So here running U, empty V, and not cold V prime. When those 3, both of them equal to 1 at the same time, this product term is going to be 1, isn't it? That was unreliable case. So I represent by this product term one of the unreliable case. The second unreliable case was this, make it different color maybe here. It says elevator running, door is open Z, elevator running U. U multiplied with Z is another unreliable case. So how I am going to write the function? Function is equal to U V Y prime plus UZ. So in here we've got product terms. So in order to represent each unreliable case, I use the multiplication of the variables, that means product term, in order to cover all the unreliable cases. I use OR operation. Not operation, in order to represent one of the variable prime, I use that, not operation. So we can say that when f is equal to 1, that is OR definition, either this equal to 1 or this equal to 1. If this is equal to 1, that means unreliable case 1. Whatever the other case is, it's going to be unreliable, isn't it? In terms of elevator reliable working, it's going to be unreliable. If this unreliable case is 1 and this is 0, still I am going to say that is unreliable. If both of them is on, that means both of them equal to 1, my function is going to be 1, that means unreliable. If both of them 0, that means there is no unreliable case, then f equal to 0, that means my system is reliable. So what we have done at the end, we had the language here, in here, let's say in this area, we've got the language used to explain unreliable case and transfer this language to a Boolean function. then when you design this function, you can make a alarm system by using a logic circuit. So that is a good example for a propositional algebra. So you can increase the number of unreliable cases by putting new ORs here, isn't it? So you're going to write each unreliable case with a product term. For each unreliable case, you're going to write a product term by using the language that you used. Okay, so that's the end of this video then.